Okay, hello class. We're here at Case Study B Notes Part 2, Case Study 2B Practice. Okay, so every time we get a new case study, we have to adjust the way that we answer, the test statistic, null distribution, p-value step. Okay, so we're going to get, for the rest of this, this note set in Part 2, we're going to get some practice looking at that. Okay, so for each of the following scenarios, calculate the p-value and state your decision based on alpha equals 0.05. Okay, so I'm going to start with just saying, hey, we have a right-tailed test. Z is approximately 1.23. Let's talk about the null distribution, calculate the p-value. The thing to know about a right-tailed test is that means that your HA has a greater than sign in it. Okay, in these first few problems where I give you the Z value, okay, we can go ahead and assume that we had a large sample. We had a large sample, we collected the data. Once we calculated this formula you see at the top, we got the following Z value of 1.23. Okay, anytime our test statistic is Z, it will always have the null distribution of Z follows a standard normal distribution, okay? N01. N01 is standard normal, okay? So anytime we have a large sample and it's talking about average, that is how you will write your null distribution. Okay, so first what I want to do is start with, well, let's write our p-value statement, okay? So it's right-tailed, and Z is 1.23. So the p-value is the probability of observing the value of the statistic from the sample, or more extreme, if HO is true. So how will we write that p-value? The probability that Z is greater than or equal to 1.23. Okay, so now what we can do is let's draw a picture of what this looks like. Okay, just kind of ignore the answer there for a sec. Okay, I draw my normal curve, okay, centered and symmetric at 0. I'm up here at 1.23. And I want to shade the area above 1.23. Okay, so now that we have our picture drawn, now's the time to go to our Z-chart. And I'll go ahead and remind you about how we use our Z-chart. So one difference between the Z-chart and the T-chart is that the Z-chart gives us the area that's less than Z, okay? That's less than Z. So if we're looking up at the number 1.23, make this a little bit smaller. A little bit smaller. Okay, so we come down here on this side and we're looking for 1.2, but we also want 1.23. So when we come up here and we look at 0.003, where do these lines intersect? Right here at 0.8907. So that's the area to the left, 0.8907. So how do we get the area to the right? We subtract from 1. Okay, so when you do that, you should get a p-value of, cut off the decimal, 0.1093. Okay, now when we have a p-value of 0.1093, is that going to be, so next thing we need to do is make our decision. Is that going to be fail to reject HO or reject HO and accept HA? Right, that's a large p-value. So our decision is going to be fail to reject HO. All right, hopefully after that, maybe kind of remember how to use our table, but let's go ahead. We're going to go through a few more examples. Okay, now we're dealing with a two-tailed test. Z is equal to 2.65. What's the null distribution? Okay, anytime we're dealing with Z, the null distribution stays the same. Z follows a standard normal distribution. Okay, how far can I go? All right. So let's start with our p-value statement. Okay, it's two-tailed, so we have to start with saying, okay, we want to double this p-value. We're going to get 2 times the probability that z is greater than or equal to 2.65. Okay, we used greater than or equal to, let me go ahead and make a note here. We used greater than or equal to because z is positive. Okay, sometimes it kind of helps to see a picture of why that is true. So if we draw our null distribution, 0's in the center. Okay, our test statistic is 2.65. Okay, and we always want to, for two-tailed tests, we want to first go to the nearest tail. Okay, and then mirror that to the other side. Okay, so for two-tailed tests, we want to, again, go to the nearest tail, double it. All right, so if we're looking for 2 times the probability that z is greater than or equal to 2.65. Okay, so can you agree that this shaded region over here is going to be the same as this shaded region over here? Okay, awesome. So since this z table gives us less than values, let's go ahead and find this area on our chart. No, oop, didn't circle it. Let's find this area on our chart, knowing that it's going to be exactly the same as the area above. Okay, negative 2.65. Nope, over here. Negative 2.6 right here. And we're looking at 5. Not 3 anymore. Okay. So that area in one tail is 0.004. Okay. So our p-value statement down there at the bottom, 2 times the probability that z is greater than or equal to 2.65. Okay. Well, that's 2 times the 2 times 0.0040. So this is one tail. Okay, so what I have highlighted in green is just one tail, but for any time we have a two-tailed test, we want to double that probability. Okay, that's going to be helpful because if you recall, in our case question 2B, our null hypothesis, we talked about, hey, it says different, our alternative hypothesis. It says that it's different from. So we do have a two-tailed test whenever it comes time to answer case question 2B. Okay, so the final answer for your p-value. So the final answer for p-value is what we get right here, 0.008. Okay, now compared to alpha of 0.05, what will your decision be? Right, we want to reject HO and accept HA. Okay, now let's look at a left-tailed test. Okay, we have a left-tailed test. Z is equal to -5. What's the null distribution? Okay, anytime we have Z, we have the same null distribution. Z follows a standard normal distribution. Okay, so let's start with our probability statement for p-value. The probability that Z is less than or equal to -5. Okay, we did less than because it's a left tail test. All right, so what does that picture look like? We've got 0 right here. We're down here at -5, and we want to shade the area that is left of -5. What's less than -5? Okay, so then we go to our Z chart. And we see that, well, our Z chart doesn't go to -5. Okay, it doesn't go to -5. So whenever our Z-score falls off the chart, we either say that it's about 0 or about 1. Okay, so what do you think the answer is going to be for this problem? Is it about 0 or about 1? It's going to be approximately 0. Okay, and we can say that because there's approximately 100% of the Z. It's not very good approximately. Okay, approximately 100% of our area is between -3 and +3. Maybe I'll go ahead and make a note of that. Between -3 and +3. Okay, that's approximately 100% of our area. So if I'm trying to get this small little area outside of my 100%, well, that leaves us with just 0%. Okay, so if our p-value is 0, what does that make our decision? Yes, p-value's low, reject HO, and accept HA. Okay, so now we're gonna go ahead and start looking at, let me see something real quick. Yeah, we're gonna start looking at, okay, well now let's actually practice calculating our test statistic. Okay, so for each of the following scenarios, we're gonna calculate the test statistic, state the null distribution, calculate the p-value, state your decision, and build a corresponding confidence interval. Okay, so we're adding on a little bit more here. So the purpose of these first 3 problems, remind you how to use our z-table. Okay, so now let's get into like, how are we gonna be answering all of these steps? All right, so I will go ahead and start with putting our formula here at the top. X bar minus mu divided by s divided by a square root of n. Okay, now just a note, just like with the t-test statistic, whenever you're typing these into your calculator, you want to be sure to do parentheses around the top and the bottom. Parentheses or brackets, just be consistent with whichever one you use. Okay, so calculate the test statistic. What do we have for number 4? Okay, we have that our HA, mu is greater than 65, X bar is equal to 70, S is equal to 3, N is equal to 60, alpha is equal to 0.01. Okay, so take a moment. I'll just go ahead and remind you of the general names for these. X bar, that's going to be your sample average. S, that's going to be your sample standard deviation. N, this is going to be your sample size. Alpha, alpha is your significance level. This is what you will always compare your p-value to. All right, so the first step is the test statistic. Okay, do we have a large sample? Yes, so we're going to be using the central limit theorem. Okay, large sample, reminder, is n larger than 50. Okay, so we're going to use the central limit theorem, which means our formula, z equals x bar minus mu divided by s divided by the square root of n. Okay, so we have a large sample, we use the central limit theorem, which means we have a z test statistic. All right, if you would, you can pause me right here, take a moment, plug in all your values, and if you want, go ahead, state the null distribution and calculate your p-value. Okay, so plugging in 70 for x bar, 65 for mu. Okay, where does that 65 come from? It comes from our HO. Even though the HO isn't written, we know what it's going to be. Okay, and we're going to divide by 3 divided by the square root of 60. And whenever you do that, you should get the number 12.91. So that's our test statistic. You're going to box that in for me so I know what your test statistic is. Okay, now we need to do the null distribution. Anytime we have a z test statistic, the null distribution is going to be standard normal. Okay, null distribution is standard normal. So now we need to calculate our p-value. And before we go use the chart to calculate a p-value, we always want to start with our probability statement. Okay, so this is going to be the probability that z is greater than or equal to 12.91. Probability that Z is greater than or equal to 12.91. All right, so if I draw my standard normal curve, all right, between -3 and +3, between -3 and +3 is where we have approximately 100% of our distribution, okay? But we're down here, oops, other side. We're down here at 12.91, okay? And so we wanna shade the area that's above 12.91. There's not a whole lot of area above 12.91. So what are we gonna say with our p-value? That it's gonna be approximately 0. Okay, and again, that goes back to whenever we have a z-value that we go to the chart and it's not on our chart, okay? Our z chart goes from -3.09 to +3.09, okay? So whenever our value falls off the chart, we either say it's about 0 or about 1. This is where drawing the picture, I feel like, really, really helps. Okay, because then we can visually see, oh, that's a really small area, so the p-value must be about 0. Okay, so if the p-value is low, what do? Reject HO and accept HA. Yes. All right, the last thing this problem asks us to do is build a corresponding confidence interval. Okay, so corresponding meaning since alpha is 0.1, then we want a 90% confidence interval. Okay, 90% confidence interval. So we're gonna start with the formula. Okay, this is the formula we wanna plug into. Now, if we kind of scroll out a little bit, we have X bar, we have S, we have N. The only thing we don't have is our table value, okay? So with the t-table, every time you do a confidence interval, you have to go to the correct degrees of freedom and pick a fresh number from the table, okay? For the z-table, we have set values that we use because the z-table doesn't change based on the sample size, okay? So I'm gonna kind of zoom in here and kind of write a reminder. So 90% confidence interval has a z of 1.645. Kind of remember these? Can you help me finish the rest? 95% confidence interval gives a z of 1.96. 99% confidence interval gives a z of 2.575. Okay, and these are set values when we are talking about z, okay? Different for t, always the same for z. Okay, I'm gonna come here. I guess I should make sure you can see the top. All right, so what are we gonna plug in for z? We're gonna plug in 1.645. And the rest of the numbers are at the top there. X bar is 70, S is 3, N is 60. Okay, so why don't you pause right here, take a moment, practice calculating that confidence interval. Okay, and when you do that, you should get 69.36 to 70.64. Okay, we always want to make sure we interpret our confidence interval. We are 90% confident that mu is between 69.36 and 70.64. Okay. Just remember that whenever you do interpret confidence intervals, I don't want to see any symbols or any statistical jargon or words, okay? You want to put it in terms of the problem. Now, this problem didn't have any context, it just gave you information, but if this problem was talking about, the one thing that's always easy for me to say or to remember is, the average time spent working out a week, okay? So we are 90% confident that the average amount of time spent working out a week is between 69.36 and 70.64. Okay, now last thing on this page is this does support our previous decision, okay? We rejected HO and accepted HA. We said that, so coming back up here, we rejected HO and accepted HA and said, yes, mu is greater than 65. And look at what we got for our confidence interval, that our confidence interval starts at 69.36 and goes up to 70.64. Okay. That confidence interval is completely above the number 65. All right. So anytime, just a reminder, when you do a confidence interval along with a hypothesis test, your confidence interval should always support the decision that you made. Okay. So I want to say I have about 3 more problems like this. Okay, I'm going to go through those problems, and at any point, I'm going to highly encourage you to just go ahead and pause and practice some of the calculations on your own and make sure that you are going to be getting the same values as me. Okay, test statistic. Do we have a large sample? Yes, use the central limit theorem. Okay, so that means we're going to use our Z formula. Okay, I give you all the values to plug in there. And after you plug those in, you should get the number 2.89. Okay, anytime our test statistic is Z, what is our null distribution? Standard normal. Okay, p-value. All right, I'm going to go over the p-value step with you because this is a two-tailed test. All right, I'm going to draw my picture right here. All right, our test statistic is Our test statistic is 2.89. Okay, so we're going to shade to the nearest tail for two-tailed and then double it. And then double it. Okay, so our p-value is going to be 2 times the probability that Z is greater than or equal to 2.89. Okay, we always want to use what the actual value of our test statistic is here. Okay, so our test statistic is positive, so that means we're going to go to the right and then double it. All right, so now we can go to our Z table and look for negative 2.89. Negative 2.8 is right here. Okay, so the area in one tail is 0.0019. 0.0019. But that also matches the area in this tail down here. Okay. So that means we need to multiply that number we got from the chart. Okay. So 0.0019 is just one tail. All right, when we double it, we get 0.0038. Okay, and we're comparing 0.0038 to our alpha of 0.05, and we get a decision of reject HO and accept HA. Okay, p-value's low, we need to reject HO. All right, alpha, I'll make a note up here every time, alpha is 0.05. So now we want a 95% confidence interval. Okay. Start with our formula. All right. What are we going to plug in for X bar? 16. What are we going to plug in for S? 0.9. What are we going to plug in for N? 75. What are we going to plug in for Z? 1.96. Ooh. So we plug in all those values, take a moment, calculate this, and you should get 15.79 to 16.2. So that means we are 95% confident that our population parameter average, the parameter is the population average, is between 15.79 and 16.2. Notice this does support our previous decision. Our decision was reject HO and accept HA. So we said, hey, mu is different from 15.7. Okay, 15.7. If I don't write anything after it, you can assume they're all zeros. All right, and our confidence interval starts at 15.79 and goes to 16.2. So yes, mu is different from 15.7 because it starts at 15.79 and goes all the way to 16.2. Okay, new problem. HA, mu is less than 362. X bar is equal to 360. S is 9.5, N is 55, alpha is 0.01. All right, so our sample size is 55. That is a large sample, so we're going to use the central limit theorem. Again, please pause at any point and practice these calculations on your own. Make sure you're getting the same numbers I am. We plug in our values, and you should get negative 1.56 as your test statistic. The null distribution for all of our problems when we're talking about averages and our sample size is large, we're going to have a standard normal null distribution. Okay. The next thing is the p-value, and we will always want to start with our probability statement. Okay, so the probability of observing the value of our statistic or more extreme if HO is true. So that's the probability that Z is less than or equal to negative 1.56. Okay, go ahead, zoom in here a little bit. This is the time where I would draw my picture. Down here at negative 1.56. And I want to shade the area that's less than because it's a left-tailed test. Okay, now I go to my chart and I'm looking for, not this one anymore, I'm looking for negative 1.56. So here I am at negative 1.5 and here's 0.06. So it looks like these lines meet at 0.0594. Okay, so that means this area here, 0.0, whoop. Let's just start that over, 0.0594. And that's our p-value. Okay, now we always compare our p-value to alpha. Alpha is 0.01, so is our p-value lower or higher than alpha? It's going to be higher, which makes our decision fail to reject HO. Okay, since alpha is 0.01, that means we want a 99% confidence interval. .99% confidence interval. We start with the formula. Always write the formula for me. Okay, and then we plug in all the numbers given from the problem. Okay, X bar is 360, S is 9.5, and the sample size is 55. The value from our Z table is going to be 2.575. All right, pause, take a moment, calculate this. And you should get 356.7 to 363.3. Okay. Again, anytime you do a confidence interval, it should always support the previous decision, okay? So we said we failed to reject HO. We did not have enough evidence that mu is smaller than 362, okay? And look at our confidence interval. 362 is within our confidence interval. So when your confidence interval contains the value of mu, that's indicative of you should have failed to reject HO, okay? Because the entire confidence interval needs to be below 3.62 in order to reject. Below, because it says less than. Okay. I'm gonna zoom in a little bit. Okay, this is the last problem that is similar to this, to the previous ones, I guess I should say. All right, we're going to start with our test statistic. Do we have a large sample? Yes, our sample size is 172. So let's use the central limit theorem. Okay, again, please pause here, practice calculating these. We get a test statistic of 1.31. This null distribution is standard normal, okay? Z follows a standard normal distribution. Okay, next step is p-value. All right, so one thing I noticed is, hey, we're dealing with a two-tailed test again. So I'm gonna draw my distribution. I'm down here at positive 1.31. So I want to shade to the nearest tail. So I'm going to go up. Since 1.31 is positive, we're going to shade to the right. And then we're going to mirror it down here for negative 1.31. So even though I'm not the best drawer and those don't look symmetric, okay, both of these shaded areas are exactly the same area, exactly the same size, exactly the same number. Okay, so when we write our p-values, when we write the probability statement for p-value, we always start with 2 times the probability, okay? So 2 times the probability of seeing our test statistic, 1.31, and then we shade to the right. Okay, so now what we need to do is we need to go find out, okay, well, what is that area? So we are going to go to negative. So, and I'm going to go to negative 1.31 because, that's not the one I want. Because this area is the same as this area, like I was saying. And our chart already gives us less than values. So if you go to positive 1.31, you're going to have to complement that number that you get. Okay. So negative 1.31, that's going to be this value right here, 0.0951. Okay. All right, so we get negative 0.0951. Sorry, got a little distracted. Okay, and then we double that value that's in the tail to get 0.1902. Okay, so just to kind of show you that even if we got the upper tail, it would still be 0.0951. We can go to positive 1.31. Positive 1.31. Okay, but remember, this is giving us the area to the left. So I'm going to have to do 1 minus. So 1 minus 0.9049 will give you 1 minus 0.9049. Will give you 0.0951. Okay, and so then we want to double that. We get 0.1902 as our final p-value. Okay, and that represents both of these shaded regions. So 0.1902, we compare that to alpha of 0.05, and that gives us a decision of failed to reject HO. Okay. So we want a 95% confidence interval. Why do we want 95? Because if you look at the top, alpha is 0.05. Okay, so when we have a 95% confidence interval, we plug in 1.96 for the z-value. So we have 102 plus and minus 1.96 times 20 divided by the square root of 172. When you solve that, it should get you 99.01 to 104.99. Okay, again, this should always support our previous decision. We said that we did not have evidence that mu is different from 100. So we don't know that mu is different from 100. And look at this confidence interval. This confidence interval for mu does contain the number 100. So as far as we know, we're 95% confident mu is between 99 and 105. And 100 is in there. So mu isn't different from 100. Okay, so that is going to end case study 2B notes part 2, case study 2B practice.